Hello calculus students, here with for 3 product and quotient rules and higher order derivatives. The main point of this chapter is to realize, and they're put separately, these rules, because when you try to take the derivative of a product, you can't just distribute. It was okay when we had addition and subtraction, but not with multiplication or division. So here's the product rule. Notice you're taking the derivative of a product, two functions. You don't just take the derivative of each. You leave one function alone, take the derivative of the other, then leave the other function alone and take the derivative of the first. Here's a proof. It's kind of a tricky proof. I'm not going to hold you responsible for the proof. I just wanted you aware of it. And notice you have to sort of subtract and add the same thing in here to get the right things factored out so that you can get the limit definition for g prime here, and here's the limit definition for f prime here. And notice the limit as delta x goes to 0 of f of x plus delta x. That delta x goes to 0, and that's why you just get f of x for that part. Let's try an example. Here goes 3x minus 2x squared times 5 plus 4x. So by the product rule, h prime of x is going to be, we're going to leave one function alone, 3x minus 2x squared, and then take the derivative of this other function. So that would just be 4. Plus, now we reverse the roles. Now I'm going to take the derivative of the first function, which is 3 minus 4x, and then leave the second function alone, 5 plus 4x. See that? See how the derivative? So basically you can do this by just writing this as two terms, and then in each case take the derivative. So we get 12x minus 8x squared plus 15 minus 16x squared, and so we get minus 24x squared plus 12x plus 15. Okay? Now, the product rule can be extended to any number of factors. So if I have 3 functions multiplied together, then I'm going to end up with 3 terms, and in each term I take a different derivative. So notice I'm going to circle in red here what I'm taking the derivative of. F in this term, g in this term, h in this term. And they give a nice example of it here, where there's the derivative, there's that 2x, there's the derivative is 1, and there's the derivative of 2. There you go. Now, product rule versus the constant multiplier rule. These two functions look very similar. Which one's easier? This one. Because this is just a constant multiplier, so the derivative of y prime will just be the square root of 2 times g prime of x. And we're done. They didn't give me a rule for g of x, so I don't have to go any further. Contrast that with this one, which now I can't think of square root of x as a constant multiplier. It's another function. So I'm going to do the derivative by leaving the first function alone, taking the derivative of the second, and then taking the derivative of the first and leaving the second function alone. So let me put my derivatives in now. G prime of x plus, now the derivative of the square root of x. Let's do a little side over here. That one, this is a handy rule to remember, and that's if f of x is the square root of x, the derivative is just 1 over 2 square root of x. That comes from the fact that if f of x equals square root of x, it's x to the 1/2 power. And now from the power rule, that's 1/2 x to the 1/2 minus 1, or 1/2 x to the negative 1/2, or 1 over 2 x to the 1/2, or 1 over 2 root x. Kind of handy though, just to have that one memorized. You can put that in your list of things. And so 1 over 2 square root of x for that. There we go. I think you really can't simplify that anymore. So very different there. I used the product rule here because there was an unknown in each of these functions. Here it's multiplication again, but because there is no unknown in square root of 2, I can view it as the constant multiplier rule. Now some people actually, I'm going to put this in green, actually do the product rule here, and then they kick themselves because they go, okay, leave square root of 2 alone, take the derivative of g of x, and now I'm going to take the derivative of the square root of 2, which is 0, and leave g of x alone. See how that's just going to fall out anyway? So that's why we just usually don't do that. See the difference, people. Now the quotient rule gets a lot more hairy here, because you have something that looks like the product rule on the top here. But when you divide two functions, you end up with a subtraction between, and that subtraction is a pain because you've got to get the subtraction in the right direction. And it's all over the bottom function squared. Here's the proof again. It takes a little clever addition inside there to get everything to work out right. So let's use the quotient rule on this one. So the derivative of y prime is going to be the bottom function g of x, that's x squared plus 1, times the derivative of the top function. I'm just going to do the derivatives in red here. The top function's derivative would be 5. Minus, now according to this, f of x, we're going to leave the top function alone, 5x minus 2, and take the derivative of the bottom function, which is this x squared plus 1. So the derivative of that would be 2x. All over the bottom function squared. There you go. So you get 5x squared plus 5 minus 5x times 2x is 10x squared. Minus minus 2 is 2 times 2x is 4x. All over x squared plus 1 squared. There's no need to expand out the x squared plus 1 squared. We're going to get negative 5x squared plus 4x plus 5 all over x squared plus 1 squared. And we can just stop there for the derivative. This does not look like it's in factor b squared minus 4ac. It's 116. No, that's not a perfect square. So this doesn't factor. That's all we're going to leave it like for now. Now, here's a way to remember the quotient rule. It's a little mock device based on this city in Wisconsin, Lodi. And I wouldn't doubt if there's some kind of high school right there. There's the running track and the fields and so forth. It's a high school. And it's called Lodi High, where all the really sharp math students go. Lodi High. Also note, is the home of one Tom Wopat of Dukes of Hazzard. Now, quotient rule, here's the mnemonic device then. The derivative of high over low, a quotient. Look at the high function and low function is low d high. That's where this name comes from, low d high. The low function times the derivative of the high function minus the high function times the derivative of low over low squared. So to get it right in the subtraction, remember low d high, low d high. Start off with low d high. Now another little tip is to rewrite before you differentiate. This function is going to be a mess if I put this 3 minus 1 over x into the derivative rules. But if I use our LCD tricks that we talked about, and this LCD is just going to be x, and it's an example of getting rid of fractions within fractions. So I'm using the base here of the compound fraction. Multiplying numerator and denominator by x, so that we change the form of the function first to f of x equals 3x minus 1 over x squared plus 5x. Now we proceed with our derivative. So for the derivative now, let's try our new low d high technique. Low, which is x squared plus 5x, times the derivative of the high function. Well, the derivative of 3x minus 1 is just 3. Minus low, we've got to switch it around. If this was low d high, now we've got to go high d low. So the high function is 3x minus 1 times the derivative of the low function, which is 2x plus 5. All over the low function squared. Okay, all that remains now is just to kind of expand and combine like terms. 3x squared plus 15x minus 3x times 2x is minus 6x squared. Minus minus is 1 times, oh, I'm sorry, this is 3x minus 1 times 2x plus 5. So we have to do the whole expansion here. This is minus 6x squared. FOIL first. Outer is 15x minus the inner is 2x, so that's 15 minus 2x is 13x. Last, all over x squared plus 5x squared. So it's 3x squared plus 15x minus 6x squared minus 13x plus 5 all over the denominator, x squared plus 5x squared. Give me another page. So we're getting negative 3x squared plus 2x plus 5 all over x, I'm going to write it as x times x plus 5 quantity squared, because maybe there's something we can factor out of this. If I take out negative 1, I have 3x squared minus 2x minus 5 all over x squared times x plus 5 squared. I was thinking maybe an x plus 5 would come out, but b squared minus 4ac is 4 plus 15 is 19. No, that doesn't factor. So that's it. Now, in a problem like this, you might want to go back to your TI-89 really quick and just, let's practice doing one calculator check. TI-89 check. Because, you know, there was a lot of arithmetic and algebra involved in this, and we might have oopsed a little bit along the way. Here's how you do it on your TI-89. You take this function. Oh, crap. Grab it. I'll grab this one. There we go. Copy this. And I'll paste it on this back here. Let's see how we compare. Paste. Nope. Paste. There we go. The derivative key, which is just to the left. The derivative key, which is just above the 8 on your calculator. Derivative, and then you've got to put in the name of the function here. So that could be a bit, but we can do it. Left parentheses 3 minus 1 divided by x, right parentheses, divided by left parentheses x plus 5, and then comma x with respect to x. And let's see what it says. Pause. That TI-89 says exactly the same thing. It even split this up, which was not necessary, but that's fine. You could have left it like this over here. Okay? Now, the next step is find the tangent line of the graph at negative 1, 1. So we've got to do two things. That is, first to actually come up with the tangent line. To use our point slope, we need two ideas. We need the slope of the tangent line, and that'll equal the derivative at negative 1. So put negative 1 into our new formula. So it's negative 3 times negative 1 squared minus 2 times negative 1 minus 5 all over negative 1 squared times negative 1 plus 5 squared. So that's negative 3 plus 2 minus 5 all over 1 times 16 all works out to be 0. So we get the slope of the tangent line equals 0. And the point on the tangent line is this point right here, negative 1, 1. So we can say y minus 1 equals 0 times x minus minus 1, or just plain y equals 0. I'm sorry, y equals y minus 1 equals 0, so y equals 1 is their equation of the tangent line. You can also check this value as long as you have in your calculator. And that's to do one extra step on evaluating a tangent, and that is, just pause for a second here. By tacking on to the end of this last calculation you did the with symbol x equals negative 1, the TI-89 will just spit out the value of the derivative at that value of x, and you get 0 much faster that way. And it accepts that. Don't put just comma negative 1 down. If you put a third argument in the derivative, it actually does that level derivative, and we'll talk about higher order derivatives in a bit. And here's our proof. There's our tangent line at negative 1, 1, looking really horizontal. Now, using the constant multiple rule, a lot of times kids mistakenly look at all these and say, oh, look at all those quotient rules I got to do. Oh, no. No, see this divided by 6, I could just divide the 6 into each, or think it as a constant multiplier out front as a 1/6, same thing with a 5/8. And here I can divide this monomial into each of these. Really simplifies things down. And in this one too, 9 over 5x squared is 9/5 times x to the negative 2, and that makes it so much easier. So keep that in mind when you're doing derivatives. Here's a little proof of the power rule using negative integer exponents. Proves that at your leisure. Now, This is what I'm looking for when you give a final answer. To simplify means either fully expand or fully factor, but don't give me something in between. That's what these things are. So fully expand or factor. Don't leave it in the sort of factored and expanded form. This is not really factored here. X squared plus 1 is not a factor. Because eventually what we want to do these is find out when the derivative is 0 or undefined, and it's going to be much handier in this format. Now, I talked about this before. If you have a monomial underneath, it's a lot easier if you divide that monomial into each. Let me show you here. 12x cubed over 6x squared minus 3x squared over 6x squared. And you see how that becomes 2x, 2x minus a half, which is equivalent to that. And when I take the derivative then would be x, the derivative should be the derivative of 2x, which is 2. And the derivative of half is 0. Higher order derivatives are when you take derivatives of derivatives. And we see that in position functions all the time. The first derivative with respect to time is velocity. And when you take the derivative of that, you get acceleration, the rate of change of velocity. And here's some notation. You see me use this prime a lot, and 2 primes and 3 primes for the third derivative and so forth. This is also called the Leibniz notation here, where we say dy over dx. This specifies both the dependent and the independent variable. So, those are all variations on how you can say the derivative. Here's an example of a second derivative in action here. Here's displacement. Take the first derivative, you get negative 1.62t. Second derivative, negative 1.62, giving the acceleration. And nice picture of the moon. Now there's some exercises I want to look at here that get a little challenging, so I already set them aside. Let's look at this one first. This is the Witches of Ignezi, number 48. Find equation of the tangent line of the graph at the given point. So we want to find the tangent line right here. It looks like it's going to be a positive tangent line. So first let's find the derivative, f prime of x, using the quotient rule. Bottom times the derivative of the top. Low d high. Low times the derivative of the top, which is 0, minus the top, high, times the derivative of the bottom, which is 2x, all over the bottom squared. So f prime of x equals, those cancel out, we get negative 54x over x squared plus 9, quantity squared. Now we can use that to actually find it, the derivative, at x equals negative 3. So we get f prime of negative 3 equals negative 54 times negative 3 all over negative 3 squared plus 9 squared. And that gives us, I'm actually going to leave it as negative 54 times 3 for now because I see some coming up down here. I'm seeing 18 squared. And we get, let me get on my calculator, and I get negative a half. And that doesn't seem to jibe with the picture. So let's go back and see where I made a mistake. X equals negative 3, maybe that's it. I put a negative 3 in here. Yeah, so negative times negative would make that positive. So yeah, we do get positive 1/2. So positive 1/2 looks pretty good for the slope there. And now to come up with the actual, I think we want the whole equation. It said, find an equation of the tangent line. So we've got the slope of the tangent line is a half, and a point on the tangent line is the negative 3 comma 3/2. So we can just use point slope. Y minus 3/2 equals a half times x minus minus 3. And you're done. As point slope, it's plenty acceptable. Now, you might have to rearrange it for the particulars in what you're doing there. So now let's take a look here. To determine the points at which the graph of the function has a horizontal tangent line. Well, horizontal tangent line means the derivative is equal to 0. Because the derivative is telling me the slope of the tangent line. So horizontal tangent line has to have 0 slope. So we start by taking the derivative here. Low, which is x squared minus 7. D high, the derivative of the top, which is 1. minus high, which is x minus 4, times the derivative of the bottom, which is 2x, over, all over, low squared, x squared minus 7 squared. So we get the derivative equals x squared minus 7 minus 2x squared plus 8x over x squared minus 7 squared. So we get the derivative is negative x squared minus 8x minus 7 over x squared minus 7 squared. Let me just check that on my calculator. And I did find a transcription error here on my calculator. This was plus 8x. And so this is plus here. Negative x squared plus 8x minus 7 over x squared minus 7. Alright, now it just remains to be seen as when is the derivative equal to 0. So when is negative x squared plus 8x minus 7 over x squared minus 7 squared equal to 0? Well, as you saw from our work with rational functions, it's just the zeros of the function will be when the numerator equals 0. Let's multiply through by negative 1. X squared minus 8x plus 7 equals 0. That factors. And it looks like we get horizontal tangent lines at x equals 7 or at x equals 1. Now, look specifically to determine the points on the graph at which the function is horizontal tangent lines. So we have to go one more step. To find the points themselves, we have to look at f of 1 and f of 7. We just show that f prime of 1 equals 0 and f prime of 7 equals 0. That is, the slopes, the derivatives equal 0 at those points. So let's find the original function again. I believe it is x minus 4 and there it is. So there's our original function. So now let's look at f of 0, f of 1. F of 1 equals 1 minus 4 over 1 squared minus 7. So that's negative 3 over negative 6, or half. So we have the point 1 comma half. And f of 7 is 7 minus 4 over 7 squared minus 7. So we get 3 over 49 minus 7, 3 over 42, and we get 1/14. So our other point is 7 comma a 14th. And you can check these on your calculator as well. I'm going to take a look at the big picture on GeoGebra. Let's take a pause. Okay, I graphed our function x minus 4 over x squared minus 7. And it's interesting, it's got a couple asymptotes at square root of 7 and negative square root of 7 vertical asymptotes. And these are the 2 points we suspect of horizontal tangent lines. Let's ask. You can actually go over here to tangents, under this thing, tangents, and we select the point and then the function. So we select the point and then the function, and there's that horizontal tangent line. Here's the point B, and then the function, and there's the horizontal tangent line for that. Verified. Notice both these have y equals 0.5, y equals 0.07. Those are slopes of 0. Okay. Let's pause. Here's another problem. At first it looks very complicated. You've given the graph of the function of both p of x and q of f of x and g of x. But you define p of x as fx times g of x. How are you supposed to find p prime of 1? We'll start by doing the derivative. P prime of x, let's use the quotient rule, or the product rule. Leave the first function alone times the derivative of the second, g prime of x, plus, now we're going to take the derivative of the first function and leave the second function alone. So we're going to multiply this by f prime of x. So to do now, p prime of 1, it should equal f of 1 times g prime of 1 plus f prime of 1 times g of 1. And you can look these up on the graph. f of 1, when we put 1 into the graph, it looks like 6. G prime of 1, well, G prime of 1 is the slope going on here. And at 1, you're going over 4 and down 2, so that's a slope of negative a half. I looked at the slope. Remember, that's what the derivative is. And luckily, they give us a straight line there. F prime of 1, at 1, f has a slope of 1. It's going over 1 up 1. So again, that's a slope. And G of 1, we put 1 into here. Here's the axis. 1, it looks like, here, let's get our axes on here. There's the x-axis, there's the y, here's the origin. Let's just get my bearings here with the origin. There you go. G of 1 looks like exactly, if this is 6, 5, 4. Yeah. G of 1 equals 4. So we get negative 3 plus 4 equals 1. Now similarly, to find q prime of x, we're going to use a quotient rule. Remember, low d high, low function times the derivative of the top function minus the high function times the derivative of the low function over the low function squared. So to find q prime of 4, we have to look at g of 4 minus f prime of 4, times f prime of 4 minus f of 4 times g prime of 4 all over g of 4 squared. And let's extend the page. And we should be able to just do this. G of 4, put 4 to the g function, that looks like 3. F prime of 4, at 4, the slope is negative 1. F of 4 goes to 7 though. G prime of 4, well, at 4 g is flat, so that's 0. All over g of 4, g of 4 looks like 3, as we said before, and that gets squared. So we get negative 3 over 9, or negative 1/3. There you go. Okay, and one more problem involving second derivatives before we move on here. And here we go. Find the second derivative of f of x equals x squared plus 2x minus 1 over x. Well, I don't want to have to use the quotient rule twice, so this is really one that calls out for changing the form. Divide through by the monomial underneath. Then you can avoid having to use quotient rule. And you get f of x equals x plus 2 minus x to the negative 1. Now you can go ahead and do the derivative. The first derivative will be 1 plus 0 minus negative 1x to the negative 2. So the first derivative is 1 plus x to the negative 2. Might as well leave it in that form as we go on to our second derivative now. For the second derivative, we take the first derivative and take the derivative again. So it's 0 plus negative 2x to the negative 2 minus 1. Or for the second derivative, we're getting negative 2x to the negative 3. That's fine. If you want to write it as negative 2 over x cubed, that's fine as well. All right, flange out.